Hello, and welcome to the third lecture and the second substantial lecture for those of you watching in the future of Statistics for Sociologists number 1, Introduction to Statistics from Basic Descriptive Statistics to Inference on Regression. So what this lecture will do is it will not finish up lecture 2 since I'm recording this lecture series basically lecture by lecture, so I'm not adapting this to a course schedule. If you're watching this and you are in my current SOS 360 class, we likely will need to cover some lecture 2 things the next time we meet. But in this lecture, I'm going to skip right ahead to item 2 here, discussing measures of central tendency numerically, understanding the mean. Then we'll move on to item number 3, measures of central tendency, understanding the median, which will lead us to a definition of skew. Then we'll generalize the median to discuss quantiles, which are something that you are probably familiar with in general. Percentiles, for instance, are a really common feature of everyday actual statistics. But many people don't necessarily understand exactly what is going on there, so I'd like to give you some intuition for that. We'll discuss quartiles specifically, and that'll then lead us to a definition of outliers, or at least one definition known as the Tukey rule. And then we'll finally define box plots. So we'll say what those boxes and whiskers are on such plots. Then we'll wrap up with the discussion of an important single number measure of spread, that of variance, and the closely related concept of the standard deviation. Again, if you're watching this in the future, you probably don't care about this. If you're in my class, Top Hat is appearing to have some kind of system-wide problems recently, so I'm hopeful that we'll be able to use it in class, but if not, we'll go ahead and find some other way to reward attendance if this persists. Likely what that will look like is a Canvas pop quiz graded on effort, not accuracy, that will be open for a very brief window of time. So here's a summary of the lecture. We're going to start with means. They're the most common measure of central tendency, which you can think of as the most typical value of a set of numbers. They work well for statistical inference, which we'll come back to later, but they're not robust to outliers. So they're a measure of central tendency that can easily be confounded by the presence of really extreme values. We'll also discuss medians, which are more robust to outliers. They quite literally capture the middle value of a set, but they won't work as well with inference, which is kind of a long story that I don't have time to get into. The important thing, though, is that they do work well for basic descriptive statistics, so we'll very often report them. We just won't use them in some later parts of the course where you might otherwise think that they would be a good choice. That'll also lead us to a formal definition of skew, which was lacking from the lecture previous. So if the median is smaller than the mean, we have a rightward skew. And then, by the way, if you ever see these kind of paired sets of parentheses like this basically means you could swap out smaller with bigger, but then you need to swap out right with left. So if the median is bigger than the mean, we have a leftward skew. I'm choosing to foreground smaller than the mean and then rightward skew because that is very common for sociological variables. But depending on the reason that you're watching this video or the specific area of social science that you work in, you might find left skews more common. So the concept of the median does generalize nicely to quantiles. So the median is a point that divides the data exactly into half. So half of the observations are larger than it, half are smaller than it. The generalization basically points us to this idea of cut points that divide a data set into distinct and equal-sized chunks, and they might only be roughly equal-sized in most applications, but that's sort of the goal. Again, we do use a few important quantiles called quartiles. Make sure not to confuse these. So the quantile is a general concept of a cut point. The quartile is a quantile that cuts the data into 4 equal parts, the 25th, 50th, and 75th percentiles. And this generates the 5-number summary, which is these 3 quartiles plus the data's min and max. By the way, when you see quartile, you might expect to see 4 numbers, but we only need these 3 cut points to divide the data into 4 sets. If you do wonder, well, what's the 0th percentile or quartile, and what would be the 4th quartile or the 100th percentile, those are generally defined as the min and the max, although not all people accept that those are meaningful concepts. So just a word to the wise. I remember when I first learned this, wondering about that and not getting a satisfactory answer. In part, it's because it's an area of math that there's some dispute about. So these provide us for the ingredients for a box plot, whether we call these things the 0 and 100 percentile or not, we include them. But box plots, although very informative, are in many ways more complex summaries of the spread of a data set. And so many times we're going to want a single number or scalar measure of the spread. And for that, we use the variance, which we'll learn to derive in this lecture, which is more fundamental and at higher levels is more common because it's easier to manipulate in proofs. But in practice, the root of that, the standard deviation, is easier to interpret and at our level is going to be more common. So let's go over some basic summary statistics for quantitative variables in more detail. So first of all, for nominal variables, we're really not going to worry too much. Only frequency or percent tabulations really make sense, so they are easy. What I referred to last time is a probability mass function, so just a list of the possible values, and then their relative frequency, so usually just expressed as a percent, is more or less all you need to report. But we have more to say about quantitative variables, especially ratio variables. Most of these apply to interval variables and some apply to ordinal variables, but this lecture is going to focus only on true ratio variables, so those that have a meaningful 0 and have equal spacing between the possible values. Meaning that when you assign the possible outcomes the integer values, so -1, 0, 1, and so on, those refer to actual real differences of size 1 between the observations. So if you have $1 more of income, then that really is $1 more of income. It's kind of hard to say almost because it's so intuitive, but again, compare it to something like the assignment of, on an ordinal scale, your pain level on a scale from 1 to 5. Depending on the day, depending on the person, the difference between 2 and 3 and 4 and 5 may not really mean the same thing. So we're going to deal again with ratio variables. So here is a summary of all of these things here. So we're going to denote the mean by this X bar here. And what that means basically is that it's the average for an actual concrete set of data. So when you see the mean referred to in this way, it's referring to the simple sample average of a set of data. There are other concepts of a mean that we'll meet later on. So for example, the population level mean will be denoted by the Greek letter mu. We'll come back to that later. There's also the median, which we'll denote this way. There's not actually a standard notation for the median, but I wanted to remind us all of how index notation works. So we can write the median as the value of X that has the index number n+1 over 2. We'll come back to that later on. We'll see that this formula here gives you a way to find which numbered observation in the set gives the median. And we've got various quantiles. I used to have a formal definition in the older set of these slides, but I want to kind of put that in the background this time because it's just very, very complicated. It's quite fun to think about, but I think it's best to avoid getting too much into the details in the main lecture. See the appendix for more. So informally, these are just the cut points of a data set. The standard deviation denoted S, and secondarily, the variance denoted S squared because this is the root of this. Again, this is the more fundamental quantity, but because S, the standard deviation, is more common to see, we write the variance as a function of the standard deviation. Sorry about that. Again, all of these are sample statistics, so don't confuse them with their population level equivalents. We'll get to them later, but just know for now that all of these pieces of notation refer only to estimates of some underlying quantity that we want to know about, but which we don't have direct data on. So, or we don't have complete data on, pardon me. We have some data, and the attempt to calculate them from the data are these things. So let's define the mean. And you might think that this is pretty obvious, and in some ways it is. So the mean is a measure of central tendency. It's equivalent to what we call the average. It's also known as the arithmetic mean. There are other kinds of means. So for example, the geometric mean, where you multiply a whole set of numbers of dimension n, and then you take the nth root of them. But the arithmetic mean is pretty simple, and we've seen the formula many times before in our lives, hopefully. So what we do is we add up, if we have a variable x and we've got n observations on x, so this is person 1's score on x, person 2's score, and person n's score, we simply add them up and then divide by n. And we can express that concisely using summation notation as follows. So what this tells us is take the sum over all of the xi's, beginning with I equal to 1 and ending with I equal to n, and then divide by n. And that produces x bar. And we will generically denote means in our class with random variable and then the bar. You might also see the mean referred to sometimes as the expected value or expectation. Technically, this is notation that refers to the population level, but you will often see this phrasing, and I want you to simply not find it scary. There's a formal definition of expectations for the population level given in the back. So why does the mean capture the central tendency? In other words, why does it give us a sense of what the most typical value of the data set is? So here's one way to think about it. It represents a redistribution of the sum of the set. So if we could somehow add up all of the values and then give them out proportionally to every person, how much would each observation get? So let's make that concrete. It might sound kind of silly in a way because this is really not going to be possible with everything. It might be possible with income, say, but not something like age. You can't actually redistribute age. But the average age of a set represents basically sum up everyone's age. And then if everyone got an equal share, how much age would they get? Here's another way to think about it. This is known as the balance point intuition. And what you can see happening here is we've got this idea that, well, first of all, we've got a set of data here. So the set of data consists of the following observations: 3 1s, 2 3s, 1 6, 1 7, and 1 10. So this basically you can think of as representing a histogram. And you can see that the mean here is 4. And although it may not be immediately obvious, I want you to convince yourself that if this number line here were a lever, it would be balanced if you put the fulcrum here, this kind of balancing item, triangular shape, at the value 4, right? And that's actually a property that it shares with real-world levers. So real-world levers are balanced when the summed product of the weights and distances from the fulcrum on either side are the same. So here, weight you can think of as probability and distance as deviation. So we actually oftentimes refer to the weight of observations in a data set. And oftentimes we weight observations differently in complex sample designs. So what that means is that when we have an observation from, say, an underrepresented group that we have made many more efforts to include, we then need to do some weighting to adjust for that. For example, you may be familiar with that design if you've taken SOS 357 at UW-Madison. But we can also think about weights as being just the probability of observing a given value. So although in most data sets that we'll look at in this class, we don't deal with problems where individual observations are assigned different weights, if you have repeat values, you can think of that as being a kind of a weight. So if you have, say, 5 observations that all have 10 years of education, then you can add them up and then divide 5 by the sample size to get the weight of the value 10. So let's prove the point here. Notice, for instance, that we've got 8 observations. So 3, 2 is 5, 6, 7, 8. And we've got here 3 observations that have the value 1. So the probability of a 1 is 3 and 8. And don't worry if you feel a little bit fuzzy with probability. For now, you can just know that probability is the same thing as percent in most empirical applications. It's, again, something that is more formally defined at the population level, but at a sample level, to estimate the probability of some event occurring, you count up the number of ways it did or could occur, and then the number of total events. So here, the total events are 8. We had 8 observations, and then we had 3 of them take the value of 1. So we have a probability of 3/8, and then we just multiply that by the value of the observation, or more specifically, its distance from the mean. So here it's got a distance of 3. So we're going to take 3/8 and then multiply it by 3. So we have 9/8. Then we've got 2 observations that are going to have a probability of 1 in 4, but it's more convenient to leave them with the same denominator. So they have a probability of 2/8, or 2/8, and they have a deviation of 1. So we've got 2/8 times 1. So we've got 3/8 times 3, 9/8, and 2/8 times 1, 2/8. Those sum to 11/8. Then notice that the deviations and the distance, weights on the other side, none of these have substantial weights because they're all dispersed, right? There's no repeats. So this has a probability of 1 in 8, and it's got a deviation of 2. So that's 2/8. This has a probability of 1 in 8, and it's got a deviation of 3. So that's 3/8 up to 5/8. And this has a deviation of 6 and a probability of 1 in 8. So it's got a total kind of contribution of 6/8. So we had 2 plus 3 plus 6 all over 8. That ends up being 11/8, which is the same as the sum we found over here. So we can see that in this case, the mean balances basically this lever, which is the distribution. That's kind of an advanced interpretation, but since we're talking about stuff that probably seems very familiar to you, I want you to start thinking about all of the depth and beauty of even some simple ideas. So even something as simple as an average, which you probably learned to calculate in like the 3rd or 4th grade, there's a lot of theory telling us why it is the case that the mean is a good estimator of certain properties of a distribution. So it's not only just a simple kind of what might be called a non-parametric statistic, meaning that you might just calculate it, and you calculate it because it seems to make sense to you, and you don't think it's doing anything particularly meaningful about the population. But there are a lot of reasons that the mean is a good estimator of many things about the population. So that's the mean. Now let's define and kind of motivate the median. So the median is the middle value of a data set. What does middle actually mean in practice? So first of all, we want to order the observations from smallest to largest on that variable. And then we want to find the individual who's got an index number of n plus 1/2. So this is not the value of the observation. It's the number of the observation when they are rank ordered. We'll see an example in a moment. You'll notice, of course, that if I is not an integer, and when would I not be an integer? Well, if n is even, let's say n is 4, then we add 1, 4 plus 1 is 5/2, which is not an integer, it's 2.5. So when I is not an integer, and thus there isn't a 2.5th individual, that's not possible because, again, as discussed in the last lecture, people don't come in parts. So the 2.5th person, 2.5th, or the 2.5 person doesn't exist. So then what we'll do in that case is we take the mean of individual I equal to n/2 and individual I equal to n/2 plus 1. So what does that mean in this context? Well, here, the example I gave before, we've got n equal to 4. So we take the second person and then n/2 plus 1. So that's 4/2 plus 1, the third. We take the third person and we take their mean. So to put it simply, if we had 4 people to find the median, we would then take the average of persons 2 and 3, which hopefully seems pretty intuitive when we say it like that. So let's practice here. Let's find the median of each data set. And note, and this is an important feature for our class, when you see a dot here, that's one of the ways that Stata represents missing values. So I'll let you pause and calculate this on your own. I'm just going to skip to the answer. So the answer is given in the comments here. So you want to pull them up like this. And I'm also going to turn my notifications to do not disturb while I'm thinking about it. So here's how we would do this in the case of x. So we've got n equal to 10. So n/2 is equal to 5. And I guess it goes without saying. So that means that n plus 1/2 is 11/2 or 5.5. That person can't exist. So we need to find persons n/2, the 5th person, and n/2 plus 1, the 6th person, and then find their mean. So we'll rank order the observations. This is a little bit tedious, but it's good to do it once in your life. So we write 5, 27, 27, 33, 45, 75, 88, 95, 95, 98. And you can see that those are the values here. And then we find individuals 5 and 6. So we count 1, 2, 3, 4, 5, 6. So that's 45 and 75. And we're going to sum and divide by 2 and get 60. Notice here that we don't worry about repeated values. So we don't fail to count 27 twice. These are distinct observations. The fact that they have the same value doesn't make them not distinct observations. It's like if you just asked the people's age, two people said 27, they're still different people. And so that gives us the median if this were, say, ages. In the case of y, we ignore the missing values, so we only have 9 observations here. And fortunately, then that means that there will be a middle number, right? So we take 9 plus 1, get 10, divide by 2, we get 5. And you can probably confirm to yourself, kind of visualize 4 people lined up, a 5th median person, and then 4 people after that. So then we can just find the 5th person's value. So we have, when rank ordered, 22, 23, 28, 39, 41 is going to be our key number, then 45, 89, 92, 94. So we've got 4 after, and that gives us 41. So that would be the median of that data set. And by the way, you can kind of think about data sets as being comprised of subsets. So when I said that data set, I presented this as one data set, but you could think about it as 2 data sets, each of just one vector, but then combined. So nothing really too complex there. So let's think about the median. So why are medians cool? Medians are cool because they're robust to outliers, which means that they're less affected by extreme value than, say, means. And that makes them what are called robust estimators. However, they're not used in inference because it's harder to make claims about the distribution of medians across many samples, which is a less good property. I think I put in the footnotes here, although I may have forgotten the justification for that. I guess I didn't, but I'm happy to discuss that with people if you're in my class and interested. But let's look at this in a little bit more detail. So I want to show why it is the case that medians are more robust, or I want to show an example. So here, I basically came up with a set of data generated at random, and there's code in the comments that will allow you to reproduce that. And then I added a whole bunch of extreme outliers. So the baseline data is this light orange, and the data with extreme outliers are noted in aqua here. And then I plotted the original sample statistics with solid lines, and then the new distribution sample statistics with dashed lines. The median are the reds. You can see that they barely differ, and the means are the black. And you can see that the mean is pulled up quite a bit. The intuition for that, in a way, is that the median is the equal areas point. So the median is the point because we can think about these percent histograms as being scaled. So even though these are percents here, this is just a scaled version of the frequency histogram. And the frequency histogram is just built by stacking squares representing individuals on top of each other. So we can think about the median as the point where half of the heights are to the left and half of the heights are to the right. That's the equal areas point. So if we add a little bit more area all the way out here, we just need to shift over slightly so the areas are basically the same, right? But the thing about the balance point is that it's not just the areas, it's also their distance from the rest of the values. And so here, because this is a not huge, but sizable, but still pretty small number of observations, but because they're so far up here on the distribution, they pull the mean up significantly. So this would be sort of the new balance point, even though these aren't very close or similar to the rest of the data. But notice that the equal areas point just shifts a little bit. So that's kind of the intuition there. So now we can go ahead and define the skew now that we've gotten the median and the mean put together. So if x bar, or the mean, is less than the median, we have a left skew. And if x bar, or the mean, is greater than the median, we have a right skew. So these data have a significant rightward skew in both cases, actually. So notice that in the original, we've got the red median and the black mean. There's a small difference. So if you just imagine the orange data, there's a slight rightward skew. But then it's very clear in the second set of data that we have a strong rightward skew because the red dashed line is far away from the red black line. This is an example of like a very stylized version of the US income distribution. As I mentioned before, many sociological variables have outliers that are larger than the rest of the data, and the lower end has a lot of clustering, which makes them right skewed by definition. So here's another example of skew. This we probably won't have time to cover in class, but I'll discuss it now. So notice here that we've got two more histograms. You might want to think about whether or not these have right or leftward skews. And I plotted in both cases. The solid line is the median and the dashed line is the mean. So this is time spent at current job from the GSS 2018. Notice here that there is a perceptible kind of tail to the right. There isn't really a similar tail to the left, which makes sense because time spent at current job can't be negative. So we've got what's known as downward censoring. That's another reason that sociological variables are often rightwardly skewed. It's that there can't be negative values. So this is a right skew because the mean is greater than the median. And then this is the number of scores correct on 10-question vocabulary tests that's given as part of the GSS. Notice here that the median and the mean are almost identical. This shape probably actually looks roughly like a bell curve, which we'll formally define as the normal probability density function later on. I mean, actually as soon as next week. So in those cases, in a true normal curve, the mean and the median are exactly the same and there is zero skew. This is just a rough approximation, but it's quite similar. So notice that in this case, we very technically have a slight leftward skew because the mean is slightly lower. And if you want to think about why that is, again, in this case, there's actually upward censoring. So it's probably not the case that people that got 0 words correct could do any worse if you had more words possible or if you could somehow get a negative score. But it is probably true that the people that got 10 words correct, there would probably be some further differentiation if you gave a 10 or sorry, a 100 or 1000 vocabulary test. So we have a bit of rightward censoring here since the total number of questions was 10. And that means that there's maybe a very slight leftward skew. But overall, vocabulary ability on this type of standardized test appears to be roughly normally distributed. So here we can see an illustration of the principle of the lever or the law of the lever. This is a depiction kind of famous from Mechanics magazine of 1824, I think, from London, of Archimedes balancing the entire globe. This is obviously not drawn to scale. He's here giant sized. And you can see that, the lever is not very long. But the principle that it's meant to illustrate is actually something that he's reputed to have said, which is that given a long enough lever, he could balance the entire globe on a fulcrum by just standing far enough out on the fulcrum. And that's sort of the idea. So it's a little bit different here because in the case of Archimedes, he's sort of thinking about adding an outlier, if you like, to the end of a distribution in order to basically get the lever to balance. Now, when we have an actual distribution, the lever is balanced by definition, so we're not thinking about adding data points out of nowhere. But the point is similar. So what we can think of here as Archimedes balancing this very uneven distribution, what's happening here is that he is a low weight observation, meaning that there's not many observations at that point in the distribution. He's just one person. And in, the kind of most exaggerated form, he wouldn't be giant. He would just be a single man. So this illustration actually kind of undersells it. But because he is at a high distance from the bulk of the other data, he is able to balance this very uneven distribution. And that's sort of the point. So low probability or infrequent or low weight observations, they all mean the same thing here, can pull the balance point or the mean far above where the bulk of the data are, here represented by the globe, just so long as they're far enough along the lever or the x-axis. You may want to stop and meditate on that a little bit. I'm sure I didn't put that from every possible angle that you could think of it from, but it's an important point to just be able to understand that on your own. So let's go ahead and generalize the median to quartiles and generally to quantiles. So the median is a special case of this more general means of measuring the spread of a data set using quantiles. Quantiles are numbers that cut our data into roughly equally sized groups. I'll discuss why roughly later on. So some common examples would be quartiles, which cut the data into 4 parts. Those are most important for us at a basic statistical level. But also common, of course, would be deciles cut into 10 parts and percentiles cut into 100 parts. In general, we can say that arbitrary n tiles cut data into n parts. So for example, 1,000 tiles, which do have a more formal name, but is a very uncommon one, not in colloquial usage, cut the data into 1,000 parts. So computer's going a little slow here. Here's an example. According to the 2018 GSS, the 3 quartiles for height measured on adults were 64, 67, and 70 inches respectively. So this means that 25% of respondents had heights at or below 64 inches, 50%, sorry, that should say heights, it says wages currently, let's fix that. So 50% had wages at or below 67 inches, and 75% had heights at or below 70 inches. So notice that we are kind of double counting observations there in a sense, because we're progressively adding more and more observations that are covered here. So the third quartile covers the bottom 75% of observations. And you might want to then think about what would this look like as a function. And this is known, if you plot it as a graph and you plot basically as many possible quantiles as you can, as the cumulative distribution, or at least an empirical estimate thereof. So this is a cumulative distribution function, something that we'll turn to several times in this class. And the cumulative distribution function capital F of x, and the capital is sort of important here, is defined as the probability that you would see an observation on the variable less than or equal to some value. This is often written with big X here to denote a random variable, and then the little x denotes the arguments to the function. So the way we would read this is these x values are the inputs here, and then as the outputs, we check and see what's the probability that the big X, or the variable, would be less than or equal to that. And we estimate probability empirically by just saying how many people in the data set had that level of height, and then we can just kind of cumulatively, pardon me, keep track of it. So for instance, here we can see that at the first quartile, which we can remind ourselves of what that was, it was 64 inches. At the first quartile, it looks like, well, by definition, 25% of people had a height of 64 inches or less, or probably fewer, we should say. And then we can see the next quartile here, so the 50th percentile, or the median, people had a height of 67 inches or fewer, and then the third quartile, 70 inches or fewer. So you can see here, I've kind of cross-hatched this graph. The vertical lines represent the height, and then the horizontal lines show you, or just draw your attention to the fact that we've got here 0.25, 0.5, and 0.75 as decimals. We typically, in fact, almost always in a mathematical context, write probability as a decimal. But you can convert that to a percent of observations, because we get that decimal by just taking the percent of observations. So notice here that these are relatively evenly spaced because height is relatively symmetrically distributed. These vertical bars do not have to be relatively equidistant. And we'll see an example in a moment where they're not. These horizontal bars do have to be equidistant because that's the definition here of quartiles. They all need to be evenly spaced because we go up by 25% each time. So that's a way to look at quartiles empirically. And we'll see later on that quantiles are actually best defined and easiest to find when we can relate them directly to values of the cumulative distribution function, or the CDF, big F of x. And again, one more time, just to tell you how to read this graph, as we put in x values, the y values tell us what percent or probability of observations had that value of x or fewer. And you can see here that we've got this kind of jagged shape here because in any empirical setting, even if the variable itself is truly continuous, as height is, we have to estimate it with discrete data. So here we only have height measured to the inches. So you can see, for instance, like let's look, let's say right here at 65, since we don't actually have people measured, say, at 64 and change inches or 66 and change inches, you can see the function changing kind of discontinuously here, right? So that's kind of a problem, but notice that because we have relatively small measurements here, we at least have inches and not just feet, we're able to get a function that looks somewhat smooth. If we could observe this for the population, it would be exactly smooth. Let's look at another example. Here, this is for the distribution of wages in the US. So this is, again, the cumulative distribution function and the quantiles. You can see marked on the graph here are the three, well, quantiles and quartiles. So the three quartiles for wages are 12, 15.75, and 22. And you may want to note here that the y-axis spacings stay the same. Again, that's just the definition of quartiles. So because we're looking at the cumulative distribution function, and the three quartiles are the points where we've got a value of 0.25, a value of 0.5, and a value of 0.75 in the CDF. These have to remain evenly spaced. But because wages have a higher dispersion, you can see that the actual x values that produce those y values are no longer evenly spaced. So this gap here is not equal to this gap here. And you can see that the gap from 0.75 to about 0.1, we would have to go more or less all the way out to 60 here, which is a demonstration. Like if we marked the 95th percentile on here, we would see that there's very uneven spacing. One more thing to note that's kind of interesting, even though wages are in reality at the population level more of a discrete variable than is height, you can see that the cumulative distribution function here actually looks smoother than it did for height, because the actual measurement of wages was done more precisely. It was done to the hundredths place than it was done for height, which was only done to the integer. And so you can see that this graph looks a little bit smoother. It doesn't, it visually has a bit of a step-like quality, but it's not very severe. One more time, the way that we read these cumulative distribution functions is this. We look and see as the x values increase, so as the possible values of wages increase, what actual percent of the data lies below or at that value? Or in other words, what's the cumulative probability? So we can see here that when we get to a little bit more than $15 an hour, we've observed half of the data set. When we get to a little bit more than $20 an hour, $22 specifically, we've observed 75% of the data set. So again, keep in mind that this is cumulative. It's not the raw probability here. It's the probability of having this value or less. So you can see that that's a reason that both of these graphs have to asymptotically approach 1, because you can't observe more than 100% of the data set. And that's a reason that we don't have negative values. You can't observe 0, or you can't observe less than 0% of the data set. And notice that these are monotonic functions as well, so they can't possibly decrease because you can't start to observe, like as you're going cumulatively up all the possible values of the data, at most you can stop observing more values, as in this region, but you can't say, okay, when I get to $20 an hour, I've observed about 70% of the data. But then when I get to $21 an hour, I've observed 65%. That doesn't make any sense because it's a cumulative graph. So those are some important facts about the CDF. And CDFs are defined for discrete and continuous variables, by the way. So let's talk about how we calculate quantiles. Here's a problem. As I mentioned before, quantiles are only guaranteed to be unique when the variable is continuous and we know the true cumulative distribution function. So I wanted to show what that might look like where you have a situation where quantiles may make relatively little sense because your data are sparse. Either you have a random variable that's highly discrete, so it takes on a limited set of values, a highly limited set of values, or maybe you have draws from a continuous random variable, but you have a literally small set of data, and therefore the random variable doesn't really fully express itself in a certain sense. So let's come down here and open stata. And we're going to run this code. We'll need to open a do file here. So type do edit into the command window. And we don't need to bother with our typical rigmarole where we save a standard header here because we're just going to use this for demonstrative purposes. So first we'll clear all the data. That will have no effect on my working session here, but it may on yours. Remember that you never want to save data in stata. You should always save a do file. So we're going to set our observations to 13. So you'll see why I'm picking a prime in a moment. And then let's generate some random draws from, in this case, a discrete random variable that is just randomly distributed or pseudo-randomly distributed uniformly across the numbers 1 through 10 inclusive. The details don't matter too much here. So let's go ahead and sum our new variable. And let's look at the percentiles that are calculated by stata. So you can see, why don't we list our data first? So we can sort them with this command, then list them. And you can see we've got 1, couple of 2s, 3, 4, 5, 4 6s in a row just through random chance, a 7, a 9, and a 10. So what did stata calculate for the quantiles and in particular the quartiles for that set of data? You can see that the 25th percentile was given as 3, the 50th or the median as 6, and then the third quartile, the 75th percentile, was given as 6 as well. So let's take a look at what happens if we ask stata what actual percents of the data fall below those numbers or are equal to those numbers. So let's come here and let's tell stata to count if x is less than or equal to this returned value of P25 or the 25th percentile. So if we come here, we need to run the sum detail command first because this return value refers to the results of a previous command, a lot like your answer function did on your high school TI-84s. By the way, to see the return values that come from any particular stata command, you can simply write help and then the name of the command, in this case, summarize, and scroll down to the bottom of the help file and you'll see them listed here. So here is R of P25, which is the 25th percentile. You can think about R as a computer function that's equivalent to the returned value. I'm going to make sure my computer is set to do not disturb here incidentally. Okay, so let's come back and let's summarize and let's count if x is less than or equal to R of P25. And so you can see that gives us the number 4. So we had 4 observations that were less than that. And then let's go ahead and display R of n, so the count from the previous command divided by the number of observations, which is 13. And you'll see here that this is actually 0.307 rounded to 31%. So what that means is that our 25th percentile actually has 31% of the observations below it with rounding. And the point here is that this is actually always going to happen. And let me show you why that is. So I'm going to modify the code here. So we can write a really quick loop. We're going to say for values I equal to 1, going up in increments of 1 to 7. You don't have to know this part. This is a bit of fancy programming. Display, oh, sorry, I wrote 7. I meant to write 13. Display I over 13. And what this is going to do is just show us for all the index numbers that you could get from a set of data of dimension 13, what the fractions or really the decimals are. And you can see here, I've made a small mistake there. Oh, there's an extra bracket. Okay, so let's run this. Okay, so if we look at this, we see that, say 1 divided by 13 gives this, 2 divided by 13 gives this, 3, and then 4 right here. So notice in this case that it's not actually possible to have an observed observation in the data when you rank order them that would contain below it, say, exactly 25%. So when we rank order the data, the choices we have are either right here, this 23, whatever observation corresponds to that, or this 31, or some kind of interpolation between those two values. And so the algorithms for interpolating those or just selecting it from the data vary, and the different ways of calculating it are different across different pieces of statistical software. By the way, I'm going to copy this updated code in here while I'm at it. So they vary across different pieces of statistical software, and the actual differences aren't a huge deal for us. So how are we going to actually do this in practice? Well, we'll either use stata, or depending on the context, and you should pay close attention to the context, we'll use this hand rule that our book gives. So what's our hand rule? First, we're going to split the data set in half. If the median is an observed value, in other words, if n is odd to begin with, we'll ignore it. Then we'll find the median of each half using the rules from before. And so when you do this procedure, you might end up with an even number of observations on both sides or an odd number. As I put in the footnote here, it'll depend on the primeness of n-1, but that's not important here. So either way, just use the rules from before. So you're either going to just locate the actual middle number as in median, or you'll take the mean of the two sort of inner numbers. So again, for example, if you have a set of 8 numbers, you'll take the mean of observations 4 and 5. And then you're done. So this third step here is really just a description of what happened. We split the data into 4 roughly equal parts. And again, you'll see my footnote here. How far they are from equal is generally an inverse function of sample size. The smaller the dimension of your data set, the larger chance there is that splitting into 4 or 10 equal parts will just result in nonsense. You can technically try to calculate an n-tile that's got larger divisions than you have actual observations. So as I put it here, you could try to take a quantile or a quartile, pardon me, for, say an observation of 2 or a data set of 2 or 3 observations. But this is really not very meaningful. There's different methods that will allow you to come up with some answer. But it's, again, as I mentioned before, really this is most useful when you've got data that, well, they're most exactly useful when you've got data that are continuous and you know the true cumulative distribution function. It's secondly most useful when, regardless of whether the variable is continuous or discrete, you have a large data set. And intuitively, that kind of makes sense because there's really not as much point of coming up with summary statistics in the first place when the data set is small. Better to just investigate it. But that said, let's violate that rule immediately and go and look at a small data set where we can calculate some of these things by hand. So suppose, ignore Shaquille O'Neal for now, suppose you take a collection of individuals in our class who have the following set of heights. And again, note that there's some repeats in here. The point, once again, is that it doesn't really matter if we have repeats. We don't change anything in how we calculate. So we've got this vector of observations here, 60, 61, 61, 65, 66, 68, 67. First, calculate the mean in the quartiles. Whoops. So first, let's count the number of observations, 1, 2, 3, 4, 5, 6, 7. So the median will be an observed value, and we come up to the fourth, which is the middle of 7, get 65. Now, calculating the mean by hand, of course, is pretty simple. You want to just sum up the numbers and then divide by 7. Let me show you how you can do this in Stata, in part because I want to illustrate later on that we'll get a different answer working by hand than Stata will give us. So let's come here. We can close this do file. We don't need it any longer. And we'll clear all. And let's write input height. And we're going to make a new variable called height. And this is an unusual use of Stata. This works best when you've got a small data set. But for purposes like this, it can be quite useful. So we've created a variable called height. You can see it over here in the variable window. And we're going to hand input the observations kind of in like a call and response fashion. So I'm going to type 60, hit enter, Stata prompts me for observation number 2. I'll type 61, I'll type 61, I'll type 65, I'll type 66, I'll type 68, and finally I'll type 74. And then I need to write end and hit enter to stop the program. So now we can find the mean, and hopefully this is the mean you'll get by hand. I also took this mean by hand, so we can kind of verify it that way. So we'll write sum height, and we get a mean of 65. And we can also check the median as well. So sum height D will give us the 50th percentile. And again, we said that the median was 65, so we get the same answer. So let's go ahead and calculate the quartiles then. So if we come back here and look at this, we've got 65. So we're going to toss out that observation. And then we've got an odd number of observations on either side, 66, 68, 74, and 60, 61, 61. So the first quartile would be 61, and the third quartile would be 68. Let's see what Stata gives us. So Stata gives us 61 in agreement with what we found, and it gives us 68 in agreement with what we found before. So we're in good news, in good shape so far in alliance with Stata, but we might find later on that this will diverge. So now we're going to have a situation where Shaquille O'Neal walks in. And let me show you how you can quickly add, probably the quickest way to just add a single observation like this is rather than start up a program, just write edit. And then down here, we can type in Shaq's height. Shaq is 85 inches tall, or at least he was when he was playing. Might have shrunk a little bit since then. And let's go ahead and try to calculate the mean and the quartiles, and then we want to see which is more robust. So again, I'll let you calculate the mean by hand. Let's calculate the median and the quartiles by hand. So now we have an even number of observations because we had 7, we'll go to 8. So we want to tab up here to the fourth and fifth values. So 60, 61, 61, 65 is the fourth, 66 is the fifth. So we'll take the average or the median. They happen to be the same for a set of dimension 2 of the two numbers, which is 65.5. And we should get the same thing here. So let's see what happens. We do get 65.5 here. And we see that the mean is 67.5. So comparing the two, we see that the median went up by half an inch and the mean went up by 2.5 inches. And that's extremely typical. The mean is generally less robust, meaning that it changes more readily with respect to a single addition of an observation that's far from the mean, the existing mean, that is. We can also calculate our quartiles by hand here too. So how do we do that? In this case, we don't have a middle observation, so we can just directly proceed to finding the median of each half. So in this case, we've got an even number of numbers, so we'll need to go ahead and find the average of the two middle ones. The average of 61 and 61, of course, is just 61. And then the average of 68 and 74 is going to be, this one might be a little bit tricky, but there's a difference of 6 between the two. So then we're going to have a difference here of 71. Let's see if that's what Stata gives us. In this case, we do get the same thing. But in principle, it's possible for Stata's results and our results to diverge. So just keep that in mind. We'll always make it clear from the context, but here we do get the same thing. So that's the way we would solve it. And as always, remember that the answers are down here as well. Okay, cool. So now we can proceed to a description of Boxplots, which are an important graphical tool that we discussed a little bit last time, but we do need to go over them in some more detail. So to construct a boxplot, we need what's called a 5-number summary and then a working definition of outliers. So to get the 5-number summary, we'll also involve something called the interquartile range. And let's go ahead and put all that together. So the 5-number summary is the minimum of a set, the first quartile, the second quartile, the median, the third quartile, and the maximum. And as mentioned before, if you really insist, the 0th percentile and the 100th percentile could be thought of as the minimum and the maximum. Again, that's contested though. Generally just don't think about percentiles in that way. So our box plot consists in the following. So on the y-axis, we've got possible values, and the box itself is going to be Q3 minus Q1, or the interquartile range, IQR for short. The whiskers are going to be defined by basically the cutoff for outliers. This is known as the Tukey rule, and the whiskers are given by the first quartile minus 1.5 times the IQR, and Q3 plus 1.5 times the IQR. And then the outliers are just values beyond the whiskers. So here are a couple of examples. You can see in this case, we've got the distribution of job tenure taken from the GSS 2018. And we've got our box here that represents the interquartile range. We can see something of a bit of a right skew here, both from the outliers and also the fact that the median is closer to Q1 here than it is to Q3. Notice also that the whiskers are not equidistant, and they're not even the same distance from the end of the box is more what I mean to say. The reason for that is that Stata's protocol is that it just plots either the actual value for the whisker, or it plots the largest or smallest, depending on which one, observation that's actually in that range. So in this case, because we've got lower bound censoring here, you can't have negative time at your current job. The whisker is truncated, whereas this up here, because we do have these outliers, you can see that the whisker must be Q3 plus 1.5 times the IQR, which is the size of this box. So the way we read this is basically our lower bound cutoff for outliers, or the lowest or highest observed value. Q1 here, the median, Q3, the upper bound cutoff for outliers, and then a collection of outliers here. And you can see over here that it's annotated, not really animated. So those are some important points about the interpretation of box plots, but let's put it in more kind of common sense language. What does this show us? What this shows us is that we've got a data set that's got some rightward skew because we've got a large number of observations at the upper end here. you could imagine that if we had a histogram and tilted this on its side, you would see a kind of characteristic rightward skew. And we'll see later on that there are means of combining box plots and histograms actually known as violin plots. What this also tells us, however, is that the data are relatively equally bunched here in the kind of middle of the data. So the most typical values don't show a really enormous spread among them. Most typical values meaning places where the great bulk of the data is concentrated. But we do have this characteristic rightward skew. And why don't we go ahead and pull up the numbers actually, even though I didn't do that. So we can do that in data here. So I'm going to use the data from the GSS 2018. And let's go ahead and sum, can't remember the variable for job. So job tenure, I think it's years job. Come down here and find it. Yeah, so this one here, so sum years job D. And you can see here that the 25th percentile is 1, and then the 75th percentile is 11, and the 50th percentile is 4. So again, there is something of a moderate skew. The difference between the 50th and the 25th percentile is 3. That between the 50th and the 75th is 7. But the primary skew here is really kind of on the upper end. And we can actually go ahead and look at that as well. So let's write hist years job, and let's make this a percent histogram. And this will take a second to load, but you can see there's a bit of a rightward skew here. So let's come back to the discussion here. So why don't we do a little bit of practice and try interpreting some box plots that are just not the ones I gave. So you may want to pause the video here and see if you can make some head or tail of this, but I'll go ahead and give the answer. So here we see the distribution of height among children and adults in the United States. This is drawn from the NHANES, or the National Health and Nutrition Examination Survey from 2017 to 18. You'll notice I use a lot of data for 2017 to 2019, and the reason for that is that most health and economic indicators in the US really kind of fell off a cliff with COVID, generally speaking, all for the worse. So we'll use data that come from prior to that really turbulent time, just kind of as somewhat more typical examples. So you can see here, of course, the spread among children's height is greater overall. That makes quite a bit of sense. Children encompasses, in this way of thinking about it, everyone from people who are less than a year old, or 0, as I noted it here somewhat confusingly, to people that are 18. And then this is people that are older than 18. And you can see here, for instance, the size of the IQR is larger, and we also don't really see any outliers here. So kind of a funny inverse way of thinking about things is that if your data are just spread out in the first place, you might have observations that seem weird in a sense, but they're actually really not canonical outliers because there isn't really a center bulk of the data in the first place. Whereas conversely, we do see some outliers for the height of adults. There's a bit of a rightward skew. But at the same time, we do see something here that looks like a relatively evenly spaced distribution. You can see that the median seems to fall relatively close to the Q1 and Q3 as well. And yeah, so why don't we take a look at what that looks like as a histogram. And you can see here that the distribution of height for children looks something like what you might call a uniform distribution, which is actually a well-studied class of distributions. So it is fairly spread out, but it's also fairly symmetric. There's not any clear outliers. So if you've got a range of values and roughly any value, or to be most precise, if it's a continuous variable, roughly any neighborhood of values is as probable as any comparably sized neighborhood, you might describe that distribution as uniform. For adults, we see something much more approximate to a classical normal distribution, or a bell curve, although we're not going to use that term after next week. Sometimes also called a Gaussian distribution. And so we see something that looks quite a bit like that. So those are some things to note. Notice that the histogram does give us the shape in much more detail that's missing from the box plot. So the box plot doesn't tell us, for instance, how the data are spread out between, say, the 25th and the 50th percentile, although that's not terribly easy to infer from here unless you happen to know where those values are. But the histograms do give us more detail. Box plots give us more precise information about spread, though. And again, we can combine them. A note on dropping outliers. So dropping outliers is something that people are often very keen to do in an undergraduate class in statistics, But note that it's an art, it's not a science. There's nothing necessarily wrong with outliers. What you want to do is use substantial knowledge of cases to make judgment calls. So here's an example of hours worked last week from the 2019 current population survey. So I went ahead and plotted here some kind of not statistical, but just sort of substantial theoretical cutoffs. So you can see here, this is hours worked last week, all jobs. Here from Juliet Shore's great book on the history of the amount of time people work. I plotted the likely human history maximum, which came shortly after the transition from feudalism to capitalism in Western Europe. I put the standard work week here, and then I put the physiological maximum up here. I actually went ahead and dropped some values that were higher than the number of hours in a week, actually. So that's an easy call to make because those are obviously data entry errors, but probably many of these things here are data entry errors or something that we should at least look askance at. However, all of these here above, say, about 49.50 would be considered outliers. So we don't necessarily want to drop these just because they're outliers. Many times you want to run an analysis with and with outliers just to see if it changes, but you don't want to drop them willy-nilly. There's kind of like two approaches here. One of them would be to consider that you may have data that are really just drawn from two different populations. So there seems to be a very tight spread around the standard kind of hours of work. So it looks like Q3 is about 40 and a slight amount of change, and Q1 is just around 35. So that means that the middle 50% of the data are really kind of conjoined in that tiny band. And even going much further beyond that to the kind of cutoffs for the traditional outliers, it's still pretty small at about 48 on the upper bound and a little less than 30 on the lower. We might consider that we want to just think of these people as being drawn from a different population, say the population of adults who don't have regular employment. Although, again, that might vary. We might want to stratify on whether or not these people are actively looking for work, for instance, or whether they might be retired or in school. So that's the more sensible approach. The approach that you don't want to take is just dropping outliers immediately and, just considering that they were errors or that there's no reason to rethink the kind of theoretical priors that you're working with. That's a reason, by the way, that Stata doesn't make it possible to easily drop outliers. So you actually have to write a special routine. I think I'll actually delay showing that, although my video on the data analysis projects goes into some detail there. So what I would recommend doing is giving that a look if you want to see how you can use return values to calculate outliers. I recommend writing a routine, or in other words, a loop that'll do that for all your variables. But there's a reason that Stata doesn't automate it. It's that it's not a good idea to just drop them without really thinking about what you're doing. So that's my note on outliers. This lecture concludes with a discussion of a measure of spread that is a scalar, or in other words, a single number, whereas the 5-number summary is a vector of values. In other words, it's a list. Again, vector has some geometric intuition that's oftentimes, in the case of correlation and regression, really informative in a way that the traditional geometry of a scatter plot isn't. But very often when you hear vector, you can just replace it in your head with list of numbers and you'll get along just fine. And that's the sense in which you should interpret it there. So let's discuss the variance and the standard deviation, which are, again, scalar measures of the spread of a data set. So when we're thinking about how to capture the spread of a data set with just a single number, maybe the most intuitive idea is to just try to find some kind of typical distance of points from some measure of central tendency. So what if we could somehow find the average deviation from the mean? And again, you'll see in the footnote here, and I encourage people to read these when they can, there's a reason that we're going to use the mean. We're already getting into the problem, as I mentioned before, that the mean, although not as robust to outliers as the median, works better in certain, well, in almost all inferential contexts. So we're very often going to use the mean in practice. So let's think about a motivating example. And this is actually going to run us a bit ashore, but I want you to see why that happens. So I'm going to kind of keep my cards up my sleeve for the moment and just play dumb a little bit. So let's take a concrete example and try to find the average deviation from the mean. So let's suppose we have the following set of shoe sizes, 6, 8, 10, 12, and 14. And let's find the average distance from the mean. So the idea will be that we will take the mean, and then we will take the deviation of each point from the mean, then we'll sum them up, and then we'll take the average. So let's start by finding x bar. And you may notice that this is given in such a way that because we've got all of these values here, you can see this median right here, the two values above it are 2 and 4 above it, and the two values below it are 2 and 4 below it. So hopefully you can just immediately see that the mean is going to be 10. Now let's try to sum up all the deviations, right? So deviations are going to be found by taking a point less the mean. So the deviation of the first person to choose size is 6 minus 10 equal to -4. And you might immediately notice from the way that I hinted at what the mean is that we're going to run aground here. So this deviation is -4, this deviation is 4. This deviation is -2, this deviation is 2, this deviation is 0. So those are clearly going to sum to 0. And we definitely don't have 0 spread here. They're not all the same data point. So that's a bit of a problem. And you may wonder, is this going to be just a weird case where we happen to have this nice set of data that the instructor deliberately put together for this purpose, or is this a more intractable problem? And it actually turns out that it's a more intractable problem. So the mean is a least squares estimator. It's actually the value of a data set that minimizes the sum of square distances from it. And in fact, it's always true that the raw sum of deviations from the mean is 0. So let's look at a simple proof. And this proof is simple enough that I want everyone to try to understand this. So if you look at this basically in set of instructions here that tells us what to do in order to get the sum of deviations. So remember how summation operation works. This tells us to sum the expression enclosed from the first individual to the nth individual. And the expression enclosed says take the actual observation of person I and then subtract it from the mean. Now, predictably enough, the summation operator can pass through sums and differences. So we can turn this, instead of one sum of a difference, into a sum of differences or a difference of sums. And then we just take each sum individually. So if we sum up all the observations, you might remember from your basic high school or probably really middle school averaging that the average is equal to what? It's equal to the sum over the number of observations. So if we wanted to rewrite the average, we could say it's the what? You may want to stop and think about that. But what you can end up saying here is that the sum is equal to the average times the number of observations. In other words, it's equal to n times x bar. Then let's come over to this other piece. So remember that we said in a previous lecture that when we don't have subscripts, in other words, we just have a constant, by definition, what that means, although it's not really by definition, it's also pretty intuitive, what we're going to do is just sum that constant by itself the number of times, or sum it that number of times. So here we've got n times to do it, and we've got x bar. So in other words, we're going to just sum n times x bar. So we get n times x bar minus n times x bar, and that's equal to 0. In conclusion, this should hopefully feel pretty intuitive. We're basically adding up the mean n times, and then we're adding up all the observations, which is also n times the mean. And so there can never possibly be a difference. So the sum of deviations about the mean is always necessarily 0. That's a pretty cool insight, I think. So what's the solution here? The solution is one that you've probably seen in high school physics and probably in high school math at some point. We're going to turn the deviations into absolute distances by squaring them and then take their mean. This yields the variance, and I'll say more in a moment about the n-1 that you see here, which is a consequence of the fact that this is the sample variance, and then we'll kind of come back to that later. So here's what we do. So we say that the variance, which is s squared here, and it's s squared, by the way, because the S stands for standard deviation. Again, we'll come back to that. But basically, the variance is equal to the first deviation times plus the second deviation, and both of these are squared, plus up to the nth deviation squared. And then we divide by n-1. You can think about the n-1 as basically being n. It's just a slight difference. But we basically take the average, right? So what we end up with in summation notation is the sum of all the deviations beginning with the first to the nth squared, and we square them before we sum them, and then we divide by n-1. So that's a way to estimate something like what we hope to begin with, the sort of average or mean deviation. And mean deviation is kind of an old-timey term for this concept. So the variance is somewhat intuitive, however, for the reason I just mentioned, that we've got an average of squared deviations. So a simple solution is that we can just take the root of the entire expression, and that gives us what's known as the standard deviation. The small correction n-1 is a little tricky to explain. It's a penalty paid for the fact that we're estimating the mean, which reduces our degrees of freedom. You can think about degrees of freedom in a variety of different ways. The most useful is that it's the number of pieces of information which are free to vary. And one way of thinking about this is that when we have the sample mean and we fix it in place, instead of having the actual mean, we are then basically constraining our data set by one piece of information. So the way to think about that is that if you have, let's say, a set of 10 numbers and you have some mean that the 10 numbers have to give, you can let 9 of the numbers be whatever you want, but that fixes the 10th in place. So the 9 numbers could be literally anything that's not infinite. They could be all over the place. But much like we saw before, as long as you pick the right outlier, you could then get the average to be whatever you want. But that does mean that you're forced to pick a certain number. So that's a way to think about degrees of freedom. Another way to think about it is that if you're thinking about these vectors as being in coordinate space, you have one less dimension. So if you have a small data set of 3 observations, that's a vector in 3-dimensional space. But if you have to have a certain mean, then basically the only actual bits that are free to vary are a subspace that's 2-dimensional. So that's the idea. But the main point here is that the n-1 is basically like n. So what you're basically doing is taking an average. So let's read this formula back from the outset. We basically start with the deviation of a single point. Let's start with the first person from the mean. We square it. Then we do the same thing for every observation and add them up, and then divide by something like n, very close to n. And you'll see, obviously, that the relative difference gets less and less important as n grows. So that gives us a sort of sense of the average deviation. But the problem is that we actually have a squared deviation up here. So we want to take the root of the whole thing to get something that's in terms of the original variable. So let's practice, and then we'll wrap up here. So let's say we again have the following shoe sizes, but now let's try to fix the problem that came before. So what's the variance? What's the standard deviation? So here, let's calculate the variance first, and this will hopefully be intuitive. But if you struggled before with figuring out exactly what was meant concretely, I think it'll be quite informative. So we take the first deviation. So that's 6, which is the first observation, minus 10. This 10 will be the same for everyone. And then we're going to square it. Then we do the same thing for the 8 minus 10, the 10 minus 10, the 12 minus 10, and the 14 minus 10. Our n here is 5, so n-1 is 4. Makes a relatively large difference here, but again, it won't be big when we have something like the GSS with 2,300 some observations. So I think it's useful to write it out like this just to see what the summation operator means. So when we write out the sum like this, we no longer need the summation operator because we've done what it told us to do. Now we can take the next step of squaring each observation. So we square -4, we square -2, square 0, 2, and 4 again. Notice that these no longer cancel out because we can no longer have negatives from squaring. So we get 16, 4, 0, of course, 4, and then 16 again. That sums to 40, and then we can finally take 5 minus 1, and we get 40 over 4, or 10. So our variance is equal to 10. And then what we can do at the end is take the root of the whole thing, and hopefully you know that that's going to be somewhere between 3 and 4, and because 10 is the closest integer to 9 in the upward direction, it should be pretty close to 3 rather than 4, and indeed it is. I'll show you again a way you can quickly check your work in Stata. Now, these definitions are standardized unlike those of the quantiles, so we shouldn't get an answer that could even possibly deviate here. Let's clear all, and we'll input shoe, and we'll say 6, 8, 10, 12, 14, end, and we'll write sum D. And here we can see that the mean is, as we said, the variance is 10, as we said, and the standard deviation rounds to the same thing that we got before. So we're in good shape there. Here begins the optional material. I'll give a brief overview of this, but I don't want to spend too long on it. But some of these ideas are kind of useful. So the first point here is that the expected value or the expectation is the way that we formally define at a higher level the mean of a data set. So this actually leads us to, from the balance point intuition to this higher level concept. You'll encounter it in all courses past this one, so I encourage you to check it out. Let's look at the expression here. So this is for discrete data, and it tells us that the expectation of a random variable x is equal to the sum from basically the first observed value up to the maximum observed value, or possible value, I should say. And then what do we sum? We sum the probability that x is equal to that value times that value. That might seem a little kind of counterintuitive at first. Why do we have this probability in here? But the idea is that at the population level, we don't have an actual number of observations. We just have possible values. And presumably, if we know the population, which is the reason we would write out the formula this way and not estimate it, we would know the relative frequency of different values occurring. So instead of saying having a data set with discrete values where we've got a whole bunch of tens, and then we just add up all the tens, we would know that 10 is a more probable value than, say, 11. We would write down the probability of a 10, and then we would just multiply it by the value. So in this case, 10 times the probability of observing a 10, and then we do that for all the possible values. Note that this formula is not appropriate in a lot of sample applications unless you do the process of calculating the probability of observing each value. So this is more for theoretical purposes. One thing to note is that this does, if you don't have any repeats, or in other words, every value is equally probable, what this ends up being here, this probability, is going to be 1 over the total number of possible values, right? And so that ends up being, in the case of the sample formula, where we don't bother coming up with the probability of each value, we just put it over n at the end. We would just immediately calculate the probability of each observation as 1 over n, and then this ki just becomes the observed values, and this just becomes the sum of observed values over n. So they come to the same formula. That's for countably many outcomes, whether it's countably infinite, or really in this case, though, this would be best for a case where it's just finite. But when we have a truly continuous random variable, even though this integral might seem a little bit scary, this basically means the same thing. So even if you don't know calculus, basically what this is telling us is take the actual value of the variable and then multiply it by what is basically the area under the curve of the probability density function. In other words, and we'll come back to this, if you think about a histogram that's got areas that are equal to probabilities, this becomes the probability of an observation, and then this is the value of the observation. So it's fundamentally the same formula as above. That's a little bit on expectations or expected value. They mean the same thing. Here, I briefly want to introduce a property of the variance that's an important tool at a higher level. It features in a lot of proofs, and it shows you a way to just think through how you would deal with some things that might seem a little intimidating at first, but ultimately become very simple. So one thing to note is that the variance at the population level just is the expected value, because that's basically a mean of a squared deviation of the random variable from the mean. Note here that there's no subscript here because we don't have a concrete number of observations, and mu refers to the population mean. So we can actually just use our binomial expansion here to expand this. We take the expectation of x minus mu squared. That reduces to the expectation of x squared minus 2x mu plus mu squared. We then find the expectation of x squared. That can't be reduced any further. And then we subtract from that the expectation of 2 times x times mu plus the expectation of mu squared. Note that we can pass the expectation operator through here. It's generally a bad idea to take the average of averages or to just add together averages at a sample level, because if you have different numbers of observations in each set, that's going to give a wrong answer. But remember that at the add together averages. So we can also do the same thing with multiplication. So we separate this out and we get basically the expectation of x squared minus the expectation of 2 times the expectation of x, and I'll take mu as the expectation of x. So a very common way of rewriting the variance is that it's the expectation of x squared minus the expectation of x squared. Okay, just a couple more things here. So there's a couple of useful properties of the mean. I'll actually kind of let everyone work through these on their own, in part because these should hopefully be fairly intuitive. I wrote these here in terms of samples, not populations, because it's kind of useful to be able to prove this to yourself, even if you don't know the kind of population arithmetic. But do keep in mind that these properties are only true if the sample sizes for the two groups are the same. Finally, you may want to work through this on your own. This requires a bit of calculus, so I'm not going to step through all of the derivations. But I do want you to know that the mean has this nice property, and it's a property that we're going to come back to, which is that the mean is the unique value that minimizes the sum of squared residuals associated with a single vector of data. And there's a variety of ways to derive this, but I'll just briefly mention that even though it might seem intimidating to take the derivative of a summation involving a random variable, it actually turns out that because of the derivative addition rule, you can just turn this into a bunch of derivatives added and then re-express it as a summation. So if you do that, you should be able to step through my proof here pretty quickly. And then finally, this last bit here on the formal definition of quantiles, this is mostly here for reference, but it turns out that formally defining quantiles and all of the different means of finding them is a bit of a thankless task. So look through this if you like. There's a really nice paper in the comments that I drew some of these definitions from, but I'm mostly going to leave that to the reader. Finally, as a little bit of a treat, there's some interesting social history of Boxplots, but I'm going to leave it there. Thanks everyone for watching, and please stay tuned.